So we are going to determine how these measurements can happen for dovetails. All right, so it's another part that you need to understand in your syllabus, how to determine measurements for dovetails. So in this case, we are going to focus how to test dovetails for precision. All right, so we are given, in this case, place identical rollers into each corner of the dovetail. Use either the hit or trial method for measurement or calculate missing dimensions. So us guys, we just have to calculate the missing dimensions. We do not have all these methods that can be that can happen in real life, but it can happen in the industry. But for us guys, we have to calculate, do mathematical calculations, finding of the unknown until you get there. So you will see, like I said, that this is just your mathematical approach, your mathematical understanding, studying of the diagram and understanding what you're given there. So they were given, calculate the diameter of the ball used in the setup of the internal dovetail E shown in this fig. So that's an internal dovetail that we have. And we want to calculate the diameter B that we have here, this one. We want to calculate the diameter from this point. It's either we are talking from up to this point or we are talking of this, as long we are talking about the diameter there. So you just need to be careful in your constructions on how you are given or the information that you have. So if you check on the majority part, we have got distances that are on the horizontal, and we have got from the starting point of the circle up to the end of the diagram represented by AD. So we can take advantage of that. From our mathematical view, we can see that the combination of A to D there is comprising of these letters that we have there. If you consider this, let us just have these steps. All right, so we are going to see that the diameter that we want, yes, it is equivalent to 2 times radius, but this is the idea. If we take the whole of this D from AD, from A to D, we are going to see that the whole of AD, it comprises of from A to B, which is the radius. So it has got A, B, plus from B to C, we do not know this, B to C, then from C to D. This is what comprises of AD. And inside this, there is a radius because we are saying from A to B, that's a radius, from A to B. Here, this one is not a radius because it's out of the circle. Take note, it's out of the circle, so it's not a radius. But from here to here, it's a radius. And also from G to B, it's a radius also. So what are we going to do? Because what we need in this case is AB, because AB is equal to the radius. AB is equal to R. If we calculate the radius, therefore we have got the diameter. All right, so meaning to say we are going to find R. So this one, let's leave it, it's there. AD is there. What about BC? We do not have. What about CD? We do not have. So we need to calculate BC. We need to calculate CD. We're done. After that, we've just resubstitute your values. You calculate your radius. You're done. All right. So let us start with BC. If you check on this diagram here, you will see that from the point G up to B here, it's a radius that we have, and this is a tangent, this one. Remember, a radius and a tangent, they meet at what? At 90 degrees. So it means G to B is going to be at 90 degrees. So this is a right angle triangle that we are formulating here from G to B to the point C. We are formulating a right angle triangle. So we can be able to calculate BC, but it will be in terms of R since we do not have that value of R. Why so? Because according to this angle of 60 degrees that we are saying here, remember, these are parallel lines. So these lines, they do not meet. So they are parallel to each other. So if they are parallel, it follows that this angle and this angle, they are equal. We are formulating what? Alternate angles there. The Z angles. So these are alternate angles. So what it means is that the whole of this angle that we are seeing here is the 60 degrees, the whole of it. But it is divided into two. I talked about this before, that if you join from the center to where the two tangents meet, and you join from the center, you're going to divide this angle into two equal parts. So it means this angle is going to be divided into two equal parts. So the 60 degrees that we see is going to be divided into two. There's going to be a 30 degrees here. There's going to be a 30 degrees. But as we are focusing with this 30 degrees inside the half of 60 is what? Is 30. So as we are focusing with the 30 degrees that is inside of the shape, this is the one that we want, not the 60 degrees, the one that is inside of the shape, the 30, inside of the right angle triangle GBD. So we can calculate BC from there. So from triangle, let us see here from triangle GBC. So if you consider the triangle GBC, you are going to see that according to the angle of 30 degrees, the radius, which is our GB, is the opposite. So if for the opposite, BC is the adjacent. So that means we can use the tan from our SOHCAHTOA concept. SOHCAHTOA concept. That's the tan is the opposite over the adjacent. So it's the tan of theta. The tan of 30 degrees is equal to the opposite, which is the radius over the adjacent. So the adjacent is the part that we want, which is the BC. This is your adjacent. So remember, you want to calculate BC. So you're going to make BC the subject, just cross multiply there. That's going to be BC times the tan of 30 degrees is equal to R. So to find BC, just divide by the tan of 30. So it's going to be R over the tan of 30 degrees. So this is how you simplify it on your calculator. This is 1 divided to the tan of 30, like this. You divide that part alone. 1 divided by the what? By the tan of 30 degrees. All right, let me just try and bring my calculator and show you what I'm trying to say here. So this is 1 divided to tan 30, 1 over the tan of 30 degrees like this. So you're going to get the square root of 3. So that BC is the square root of 3. So BC is going to be the square root of 3, but multiplying what? Multiplying R. Remember, we simplified this and it gave us square root of 3. But there's an R there that we are multiplying. So yes, you can write it as a decimal, which is fine, or you can leave it like that, or you can simplify it as a decimal. It's up to you in your simplification on that part. So up to you there. All right. Now on this part, we are going to say that, like I said, we need BC. So we've got our BC here. So we are going to need BC. We now have it in terms of R. So BC in terms of R is the square root of 3 times R. So this is our BC. This is how we could calculate this BC. So with this BC, let us consider what is missing also. What is missing here on our formula, because we now have this BC, it is CD. From C to D, this one. From C to D. All right, this is the distance that we want from this point C up to D. All right, I want this one. Let's hope it's going to work. From C up to D, like this. This is the part that we want. All right, so don't consider that one. It's a lie that you see there. Us, we need the exact thing. All right, so this one, it's just a lie that you're seeing on this one. All right, so this is the distance that we want. So here we are done. We don't consider this. Let us just focus with this part alone. Okay. How can we calculate this distance? All right, one, we can see that this is 35 millimeters, which is the same as this one, from E to C, this one, from E to C, which is 35 millimeters. All right, but if I consider the wall of this line, if I take it straight up to this point here, going down, all right, just going up to this point. Okay, let us just consider this line here. You will see that this is where our 45 millimeters starting from. It is starting here, ending up here. So the wall of this line here, it is consisting of the 45 millimeters. So it is consisting of the what? The 45 millimeters. So what we need is to remove this point here from this point up to this point. If we remove this point, we are left with the B, with the C up to D. We are left with the C up to D, this one. So we need to remove this point here. And this point, it corresponds here with what? With the E. This point C, it corresponds with F. So we simply need to remove EF. From where? From 45 millimeters, we obtain CD, because we are saying from E to F, if you take this E to F, plus from C to D, because F is on the same line with what? C to D. If you take this, you must get the whole of this what? Of this 45. So as we want what? What do we want? We want CD. So that is, we have to subtract this, take this to the other side, you transpose it, it becomes what? A negative. So CD is going to be 45 minus EF. But are we having EF? That is the question. No. So you see, it's all about mathematical approach. You find this, or you see that I don't have this, I have to find it again. So we are seeing now that we do not have EF. We have to calculate EF from where? That is where this triangle now plays a role. The triangle ECF, this one. It's a right angle triangle, considering that this is a vertical line and a horizontal line. They meet, horizontal line and vertical line, they meet at 90 degrees. And we say the wall of this is 35 millimeters. So it also means this is 35 millimeters. So from triangle EFC, from triangle EFC, we can calculate what? We can calculate EF, this one. So we have to calculate EF. So using triangle EFC, this one, from point E to F and down to C, we saw that this is 35 millimeters. So we've got 35 millimeters there, and this is a right angle triangle, horizontal and vertical line. So this is your EF. You want to find this EF given an angle inside there of 60 degrees. There's an angle already inside. So you see that this is the opposite according to this angle. This is opposite, and this is the adjacent where the angle and the 90 degrees lie. So that means we're going to go back to the SOHCAHTOA concept. Tan opposite over adjacent. The tan of 60 degrees is equal to the opposite 35 over the adjacent, which is EF. So just like the previous case, we cross multiply, then divided. We saw that EF is going to be 35 over the tan of what? Over the tan of 60 degrees. So this is our EF. So by doing this, we are finding the exact value of what? Of EF, which is going to be 20.207 millimeters. So that was going to be our EF, 20.207 millimeters. So with this EF, we are going to calculate CD, because CD is 45 minus EF, which is 20.207. So that means our CD is going to be 24.793 millimeters. So that is what we have there. So everything is there. We have got our CD. So this is our CD. We have it. So our CD is 24.793 millimeters. So with this whole information, all these calculations that we have been doing, why? What is the purpose of this? It is that we can be able to manipulate that equation that we have been talking about into, or in making R to be the subject. Remember, we need the radius. By finding the radius, we have got the diameter. So from this equation, we have got AD in this case. AD, remember, our AD is given from the point A to D, this one, A to D. That is the whole of what? 65. So 65 millimeters is equal to AB, which is the radius. So that's the radius, plus BC. We calculated BC and CD. So there we are just simply substituting our BC in terms of R. So that is the square root of 3 times R plus CD, which is 24.793 2.793. All right, so just transpose the 24 comma this side is going to be a negative. So it's 65 minus this. So you are going to subtract these two, and that is going to give you 40.207, which is equal to, here you just add 1 plus the square root of 3, since R and R are the same there. So you just add 1 and the square root of 3. So 1 plus square root of 3 is going to be 1 plus square root of 3, which is, as a decimal, is 2.732 to 3 decimal places. So that's it. We can have our radius, guys, by dividing this by 2.732 both sides. We have our radius. Why are we focusing on the radius? Because that is where our diameter is going to be taken from. So with a radius of 14.717 millimeters, we can find our diameter. Remember, I said before, diameter is twice the radius, 2 times the radius. So it's going to be 2 times the radius of 14.717. There we have got our diameter. That was the question. Calculate the diameter. Just like that. So this is 29.434 millimeters. All right, so the dovetail is actually one of the easiest. If we are to consider precision measurement, this is one of the easiest part. You just have to know the steps, your mathematical calculation. In fact, just study the diagram, all right? If you're someone, make sure that you study this diagram that you are given. It's all on the diagram. Are you able to analyze your diagram in this case? If you are able to analyze this diagram, therefore, you are able to attempt or answer any question. So that was our question to calculate the diameter. Let us check another question also and see what's the relationship. You see that it's almost one and the same thing. There we are given external dovetail calculation if both angles for external dovetails in Fig 4.18 are 45 degrees. All right, these angles are 45 degrees both. So you've got an angle of 45 degrees, which means this is the one that we are considering here. That is 45 degrees. That is also 45 degrees there. So calculate the distance x. We're supposed to calculate this distance x, which is from the end point to the end point of our rulers there. Okay, that's it. That's it. Where is x found? If you just ask your question ask yourself a question like that, you are done. Where is x found? All right, x is found on the horizontal line. It lies on this horizontal line. That is where x is, on the horizontal line. So we have to consider, or we have to work focusing our sight on the horizontal line. Okay, this is what I'm trying to say. Focusing on the horizontal line. Remember, we are supposed to find x. On the horizontal line, you'll see that there is a distance of 125, which is starting at the end and going to the end. So this is the best to focus or to deal with. So from the 125 millimeters, you are going to see that, remember, we have to calculate x. So the 125 millimeters that we are seeing here, all right, it is going to be a combination of a lot of things here. 125, it is going to be x is going to be there, but there is something here from here to here. We have got something that is not ordinary there. Let me just try and do this. Maybe you might get me. If I do this, sorry for that. All right, let me just try and do this. Okay, we've got something that is not ordinary here, because if we consider what is happening, if we take this one straight, I just want to take this one straight like this. Sorry for these measurements that are being shown by this thing, guys. I don't want these measurements. I don't want these measurements to show, but they keep on showing. I don't know what's the problem. But like I was saying, if you take this and you also do the same here, you see that there's something that you're considering. Why is it not coming now? All right, like this. I'm gonna take it straight. All right, why is it so slanted like that? It means it's not that straight like this. All right, guys, what am I doing? What am I doing? Okay, like this. Sorry for these centimeters that are showing, guys, very sorry. Okay, So if you consider it that way, you see that this is a radius from, because we are considering the horizontal line. So you have to focus our sight there. So this is a radius from this point to this point is the radius, which is the same as this point up to this point. There's a radius there. Okay, I hope you're together there. We have a radius, which is the same thing from this point here up to this point. The center, it's a radius, which is the same thing. There is a radius there. So meaning to say there is a distance that is remaining. This is also a radius. This is also a radius there. It's also a radius. From the center to this point, guys, it's from the center to the circumference, the radius. So meaning to say there's a distance that is remaining, and this distance, if you check it properly, it is distance that is taken from the center to the angle dividing here. It's going to divide. We are talking about this distance that is remaining, this one, the horizontal one, this one. So let us just say I have got point, I can just name 2 points, E and F. All right, that one, it's actually up to you. You can name your point E, you can name another one F, you can name A, B, you can use anything that you want. All right, so I'm going to take this, let's say this will be the point. This is the major point that I want, this one at the center. So I'm just going to take A, B, C. A, B, C. So it is the same thing that I'm going to also have this side like this. So it's going to be A, B, C. So as you can see, it's an identical. This, what we have this side is the same as this one. So it's one thing there. It is just one thing. So when you talk about one part, when you talk about this AB, we have talked about this AB. So just focus on one side when it is like that. So let us combine, because I think we've got everything on this line. We want an equation first. So you're going to see the 125 is going to carry from A to B. All right. So it is going to be A, B plus, it is going to carry the radius, is going to be included, plus the radius, plus it is going to carry this distance in between, which is our X. Take note, it's going to carry X, plus it is also going to carry the radius, this one. That's a radius there, plus also the AB, the same as this one, which is our AB. So like I said, use one thing so that you don't get confused. So as you can see, this AB and this AB is the same because these are identical. So it means we got 125 is equal to AB plus AB. That is going to be 2ABR plus R is going to be 2R plus what? Plus X. So as you can see, guys, this is what we want. If we can find AB, we're done, because the radius we have from where we are given the diameter of each, the diameter, these are identical, so we've got same diameter. The diameter, if the diameter is 15 millimeters, therefore the radius is going to be what? Divided by 2, which is 7.5 millimeters. So we have the radius. We do not have X. This is what we need. The question needs us to find X. So we have to calculate AB from where? Where can we calculate AB? If you check this triangle here, which is the same, because the AB, this side is the same as AB, that other side. We said this consists of the radius, this one. And we know that our radius is given. So we're going to take this as a right angle triangle, this. So you're going to calculate AB here. So calculate AB. All right, calculate AB. All right, because I've increased this too much, let me reduce it. All right, so to calculate AB, we are going to have this right angle triangle ABC. So we're going to use the right angle triangle ABC. It is right angled at BY, a radius and a tangent. They meet at 90 degrees. I explained that. So this is A, this is B, this is C. Where BC is radius, this BC, R is equal to BC. So meaning to say we've got radius, and you said radius diameter divided by 2 is what? 7.5 millimeters. So we need to calculate AB. Given an angle, what is going to be the angle? Remember, the wall of this angle is 45. And I said from the two tangents that are there, this is a tangent, this is a tangent. So if the line is drawn from the center, it divides this angle into two equal parts. It bisects that angle. That is the properties of our geometry. So if we divide this by 2, that means we're going to have 45, which is 22,5. So the angle there is going to be 22,5 degrees. So according to this angle, to find AB, we've got the opposite. AB is the adjacent. So which ratio that uses the opposite and the adjacent at the same time? From the SOHCAHTOA, opposite and adjacent, that is the tan. So the tan of theta, which is the angle of 22,5 degrees, is equal to the opposite, which is 7,5, over what? The adjacent, which is our AB, to be calculated. So that means we can calculate our AB by our cross multiplication, just like the previous case. That's AB, the tan of 22,5 degrees, is equal to 7,5. So to find AB, we're simply going to divide by tan 22,5, that's 7,5 over the tan of 22,5 degrees. So that's it. We have our AB from there. That is the idea there. That is the idea. So this is going to give us 18.107. That's 107 in millimeters. Are we done? No. We have to come back to the equation now and find what we are supposed to find here. So from our equation, I'm just going to take it this side. Sorry for that, guys. We said 125 is equal to 2 times AB because they are the same. The AB that we are seeing this side is the same as the other side. What we have on this side and what we have on this side is the same. Just like the radius and the radius, they are the same. That's why we have to multiply by 2. So meaning to say, we are going to just take this into consideration. So this is going to be 2 times our AB. Remember, we calculated AB, we got 18,107. Plus 2 times the radius, we have the radius 7,5. So that's it. That's it, just like that. So plus x, which is the last part here, which is x. So plus x. So we can be able to calculate our x. So if we simplify everything on the right-hand side, that was going to give us 51,214 plus x. So to find x is simply transposing this to the other side of the equation so that it becomes a negative. So that's x is going to be 125 minus this. 125 minus 51,214 is going to give us 73,786 in millimeters. So that is the idea there. That is the idea. So you see, it's just about your mathematical approach. How are you going to approach this? How do you understand your constructions, your geometric constructions, all those things? How do you understand? And with that, you can be able to answer any questions. So let us just consider 1 or 2 questions so that we finish up. But if you check some of these questions, we already have talked about this before. These are the typical questions. Even if you check your question papers, your past exam papers, you see that they are asking typical questions like these ones. So you just need your formulas. With your formulas, you can be able to answer any question like I said before. All right, so this is what we are given on activity 4.6. We are given the internal dovetail on the other part. Calculate the distance x from the internal dovetail shown in fig 4.21. So that's an internal dovetail that we have. And we need to calculate x. Look where our x is. So x, again, it's representing a horizontal distance. So you can take note of these horizontal distances. If we take a consideration of these lines, you'll see that x is actually going to the end, meaning to say the rulers are also part of our calculation. They are part of our calculation there. So we need to focus on this and tell, according to our information, we are supposed to tell, according to the information that we are given there. And also the other thing, all right, these are, all right, that is, okay, no problem. Let us just do this together, guys. Let us just do this together. No problem. I just want to have this. Okay. So if I consider this here, if I consider this part, why is it like, okay, this is the reason. You see, guys, when I prepared this, I prepared something. You see, I missed this question. I was like, why is this values like? What is happening there? Okay, no problem, guys. Very sorry for this. Let us talk about this one first. All right, very sorry for that. I was like amazed. What is happening on my preparation? Because I knew how I prepared my class. All right, no problem. So this is it here. We are given this one. We're going to go to that one later after this. For the two inclined faces shown in Fig 4.20 here, calculate the distance x. There is a distance x there. So if you consider what we have, we've got one, the different angles that we are given there, but these are identical. The diameters are the same. And if you consider our x is from the end to the end, from the end here up to the end here, that is where our x is. So considering or working with our distance, this one of 125, this 125, this one, you see that it's going to be limited because it is limited up to this here, up to this here. And there's a certain distance that is not there, this one. There's a certain part. All right, let me do it this way so that you understand me. Let me extend these lines first. I hope you understand me. If we extend this line a little bit further like this, just going up. All right, just going up. Then we do the same thing this side, just going up. Guys, I don't want these centimeters. If someone who can help me with a better whiteboard, please do so. All right, so this is what we are having here. If you consider your AB, it is from this point here up to this point. That is where this is ending. I mean, the 125, it is from here to here. So you have to be very careful there. All right, let's consider that. At least there's a hint that you're seeing there. If you're someone who have been working with these questions, you can see a hint there. All right, no problem. Let us do this. So like I said, from the 125, remember, we want to calculate x. We do not know x. So always work with the biggest distance that you're given there from 125 millimeters. All right. From the 125 millimeters, we are going to see that it is a combination of 125. It's a combination of this A to B, this one from A to B, plus from B to this point here. From B to this point, it is the same as this point to this point, which is from the center. So it is a radius. So we've got a radius plus from this point up to this point, what we have got x. So x is involved. Then we move from this point up to E, from this point up to E here. What do we have here? That's a radius again. So we've got a radius. Then we have got from this point up to the end here, where this line is ending there at what? At F. So this is EF. So you're going to add EF. But there's something now about these letters EF and AB, this one. Here we do not have a problem because here we've got the diameter, so the radius is already there. So the radius is fine. But AB, how are we going to find this just from this corner here up to this one? How? How is this possible? So you see that we are going to need this angle of 52 degrees. All right. From your constructions, if you are to do this, let us increase a little bit. Let us start by AB to find AB. To find AB. All right. So to find AB, let us take this one. If you consider this perfectly, you will see that I have a radius here from this point up to this point. That's a radius, this one. It's a radius, which is this divided by 2, guys. It's going to be what? 12.5 millimeters. All right. So this is 12.5 here, millimeters. All right, which is our radius. But if I consider this, that I have got a tangent because this is a tangent to the circle, a tangent again. Remember what I said. If you draw as a line from the point of where these two tangents meet to the center, it is going to divide this angle into two equal parts. This angle and this angle here is going to be divided into two equal parts. It's going to be divided into two equal parts. So what is going to be this angle? Because as we can see, we can formulate a right angle triangle. Why am I talking about a right angle triangle? This is a tangent. A radius. It meets a tangent. They meet at what? At 90 degrees, a radius and a tangent, tan chord theorem. So it means we can have AB. Remember what I said, the whole of this angle can be obtained from 58 angles on a straight line. So that means 180 minus 58 degrees. We have got the remaining of this angle here, the whole of this. But because it was taken from a tangent and it's from the radius, it's joined to the center. This is going to be divided into two. The angle that we have this side and the angle that we have inside of the triangle, we divide it by 2. So thus we have the angle now that is affecting this part. So that was going to give us 61 degrees. So meaning to say inside of this triangle, there's an angle there of what? 61 degrees. So using that concept now with a right angled triangle concept, we can be able to calculate our AB in this case, because we have got a right angled triangle from the center. Let's say this is O, from the center to B, then to A like this. This is, let's just say O, B, and A. From the center to B, that is the radius, which is 12,5. So I've got 12,5. The angle there, remember we divided by 2 and we got what? 61 degrees, that one. 180 minus this, then you divide by 2. So you want to calculate AB, and it's a right angle triangle. So you can be able to calculate AB. All right, from which concept? We have got what here? We have got the opposite adjacent. So that's the tan. We talked about this before. The tan of 61 degrees is going to be opposite 12,5 over the adjacent, which is our AB. So this is over 1. So you're going to cross multiply, then divide, guys, from those mathematical calculations. It's going to be 12,5 over the tan of 61 degrees. So that's it. We have got our ABs there. So divide this, we are going to obtain 6,929 millimeters. So that is how we could have calculated the point from A to B. All right. So as we saw that our AB is going to be what? 6.929. So you do the same thing to calculate EF. As we saw that here, we are going to need EF from our distance. We're going to need EF. So how are we going to calculate EF? EF is the same thing again. We are just simply going to have a right angle triangle, just like the previous case. This is it. This is our radius, 12,5. We've got a right angle triangle. We do the same thing from our tangent concept. There's a tangent there. So this is 62 degrees. We subtract it from 180, divide by 2. These two angles are equal. This angle and this angle inside of the triangle. So 180 minus 62 degrees divided by 2. We talked about this. That will be 59 degrees. So the angle inside is going to be 59 degrees. So having a right angle triangle, guys, it's an advantage because you can use that to calculate any side from our trigonometrical ratios. This is 90 degrees. So just say this is O, which is the origin, O to E, the center, to F. From O to E, that is your radius. This one represents the radius, which is 12,5. So I have got 12,5 there. Then I want to calculate EF. So what is going to be EF? So according to the angle of this time, there's an angle different, 59 degrees. So I've got opposite adjacent. Again, the same ratio, the tan. So the tan of the angle theta is equal to the opposite, which is 12,5 over the what? The adjacent, which is what? EF. So just like the previous case, cross multiply, then you divide, you are going to see that at the end, EF is going to be equal to 12,5 over tan, over the tan of 59 degrees. So this is our EF. All right, sorry for that. So that is going to be EF. which is going to be 7,511 millimeters. So we have got EF here. So everything that we need is there on our diagram. That's 7,511. So like I said, everything that we need here we have. So we can be able to calculate the distance X. We can be able to calculate this distance X. So it's going to be 125 is equal to AB. We calculated AB 6.929 plus the radius, which is the same. Here you can even write as 2R, which is fine. Or you can just take your radius. Remember your radius, when you divide it by 2, it was 12,5. So this will be 12,5 plus X, which is the one that we are supposed to calculate, plus the radius. We still have the same thing, 12,5. Remember our radius is 12,5. All right, plus EF. We calculated our EF. We got 7,511. All right, so that's it, guys. We are going to add everything there. This one, add to this, add to this, add to this. You remain with what? You remain with X there. You are going to remain with X. So that was it, guys. You're going to obtain 39,44. So that was going to be 39,44 plus X. So to find X, simply transpose this to the other end. It becomes a negative. So X at the end was going to give us 85,56 if you subtract properly. Just like that. Just like that. So guys, more questions, more questions. Let us just finish up. We know that on this one, we are done. We are just going to work with more question papers. But if you check, these are actually typical exam questions. Some of these questions that I'm actually doing right now, these are exam questions. If you check these exam questions, they've actually, and these guys, they just change here. They can change here to write 120. Another question paper, they write 130. They leave everything. Guys, our department is not working. But that's it. It's an advantage to you guys because you have got the upper hand when it is like that. Revising just 5 question papers perfectly, you know that you are done. Each subject you go revise, you are done because they are just repeating. Only changing. Some of the questions they do not even change anything, just as it is. You see this question, guys, I'm telling you, check all your question papers. You will see this question as it is. Not only 1, 2, 3, 4 question papers, same question, same values. So do revise as many question papers. You'll see that you are done because they do repeat. So it's an advantage to you guys when it is like that. All right, calculate the distance X. Again, we need X, but this X is covering everything up to the top there. All right, what is it that we have? There it is at the end. This one is also at the end. This is 65 degrees. All right. So let us just consider one side. We cannot just consider one side because this is also 65 here. This is also 35. This is center, radius, a diameter 25, 125. Okay, let's study. Let us study. Let us study and see what is building up this X. This X is built up with, let us start with the end points there. X is built up from here to here. But if you see here, there are 2 things to be considered here. There are 2 things. The radius, which is a continuation there, there's a radius. From here to here, there's and a certain distance that is remaining. Are you seeing that? Let me show you. Let me show you guys here. Here. If you do it this way, let us just have it something small like this. All right, this was the part of the radius, this one. So if you consider, you see that there's a gap there. It is the same thing also this side. There's going to be a gap. There's going to be a gap there. So you see that there is a radius there from this point up to this point. This is from this point up to the center. So there is a radius. Then what about this one that is remaining there? What about that? Where are we going to have it? And what can we do? We do not know this. So this distance, this one in between, I'm just going to call it y, guys. Let me just call it y. All right, let me just call it y. So this distance, you see, it is the same thing as what you're going to have also this side. So I'm not going to talk about this side. You just know that what you've done here, you're going to do it on the other hand. So it means if we were to combine this, before we talk about this y, let us talk about the x on its own. So it means x was going to be equal to the radius. We're going to take this radius plus this y, this one, this distance that we do not know there. That is y plus, all right, we are here at A. So at A, we are now considering the whole of this distance up to the end point. You're considering what? The whole of this 125. So you're going to add 125. You are now at this point. So this side here, it's a repetition of this side. So what are we having on that side? We have got y, and we also have the radius. So it's going to be y plus the radius. So at the end, x is equal to r, and r, that is going to be 2r plus y, which is going to be 2y plus 125. So we have the radius. We just do not have this y. That was the idea of the person. All this that they're asking us, guys, is to just, do you know, and how are you going to find this y? That is the purpose of this question. The major purpose of this question, that is what they want. All right, remember your y here because I'm going to make some adjustments here. So let me also do this way, connecting to like this so that you'll be with me. All right, so this is the distance. Oh, sorry for that. This is the distance that I'm talking about, this one. Remember, this is the radius here. We are fine with this. So the y is this one, the distance in between this one, in between here. This space that you see, this is the one that I'm calling y, this one. This is my y. Okay, where are we going to have this y? Guys, is there any way? Maybe let me write it on top here because I'm going to need this space down. This is my y here. I'm just going to put it there so that you see. So where am I going to have this y? If you take into consideration, you see something here that there is a radius here to be considered. Remember, with the reason they gave us this one, this length, you are also supposed to think about that. Why is it that they gave us that length? Why is it that they gave us that length? All right. It is because we can use this with the point E and C, this one. I want you to see, if you calculate the whole of this side, CD, this one, from C to D. Okay, let's say I have this one, CD. If I have CD, how is it going to affect us to find this one? It means that, take note, where A and B, this one, it was an inline, this A and B. It was like this. It was actually inline to the same point. Where D is, it is at the same point. It is at the same point. So if I have this CD, and if I have this AB, this one, from A to B, and I have this C to D, can't I have this remaining distance, this one? I can have it this one. So y is simply equal to the difference between the whole of this line CD minus what? AB. If we remove that AB, we remain with y. That's it. We remain with y. So the question is, where are we going to have these two now? So you see, guys, the idea, you formulate this. After this, you have to formulate another thing. So the question is, where am I going to have CD? Where am I going to have AB? All right, CD, if you consider this taken from the center, from E to C to D like this, it's a right angle triangle that we are formulating. And from the tangent concept, we said a tangent, and a line is drawn from the center to where the tangent meet. It means it is going to divide these two angles into two equal parts. So if the whole of this angle is 65, it means the whole of this angle is also 65. So this angle inside of the triangle, you're going to divide by 2 because of what? That concept that I've been explaining about two tangents that are being drawn where they meet, and you draw a line from the center, it divides. So this angle and this one that is outside here is going to be divided by 2. So how do you find this theta now? Just going to divide by 2. 180 minus, this one is 65 divided by 2. 65 divided by 2 is 32.5. So this will be 32.5. So we've got the angle there, 32.5. Remember, EC, from E to C, it is the radius here. E to C, it represents what? The radius. Half of this diameter, our diameter is 25 millimeters, so the radius is going to be 12.5 millimeters. So thus we can calculate CD. So from there, let us calculate CD. So calculate CD. Opposite, adjacent. So calculate CD. All right. So from the opposite adjacent, tan, so it's going to be the tan of 32.5 degrees is equal to the opposite, which is 12.5, the radius, over CD, the one that we want, or DC. So that's it. We can be able to calculate this, cross multiply this and that, guys. We talked about this. It's going to be CD. The tan of 32.5 is equal to 1 times 12.5, which is 12.5. Then you divide by the tan. So that means the CD is going to be 12.5 over the tan of what? Of 32.5 degrees. So that's it. We have got our angle there. So it's just a matter of your playing around with these calculations, your triangles, and so forth. So that was going to give us 19.621 millimeters. All right. We have got C to D. What is remaining? To find this smaller distance, Y, it is AB. So where are we going to have AB? If you check, AB is here on top, this one. This is where we have our AB. This is where we have our AB. So again, we're going to take this right angle triangle from A to D to B like this. We are formulating a right angle triangle there. So what's the concept? Remember, all of this angle is 65 degrees. So if this whole angle is 65 degrees, let me do it this way. If this angle that we are seeing here in between here is 65 degrees, the whole of this angle is 65 degrees. What does it mean to you? It means also this one is going to be 65. We are formulating a Z angle like that. Alternate angles, they're creating a Z. So the angle at A is going to be also 65. So we can take that as an advantage to say we have got the angle at A. Remember, all right, our CD, we calculated it, this one. Let me just write aside. We got 19.621 millimeters. All right. So we are going to use this information that we have from this right angle triangle ABD. So from triangle ABD, we are going to find this AB. Remember, we want to remove this AB on top. AB. So if you consider it's ABD like that, it's a right angle triangle, that one. Like this, from point A to point B to the point what? To the point D. AB is the one that we want. So we're going to calculate this at an angle, this one of what? We said if this is 65, this is also 65, like I said before, this is also 65. Or you subtract from 90. This is 90 degrees. So 90 minus 65, you use this angle that is inside here. Still one and the same thing. But as for me, I'm going to use this 65. All right. So then this is right angled. Remember, this BD is the same as this 35. So it means we have our BD here, which is same as what? As 35 here. That's the idea. So with this information, just like what we did, those ratios we calculate is the same thing that we are seeing here. From this angle, this is your opposite. So there we have got the opposite. What about AB that we want? It's our adjacent. So it follows that the tan of theta, the tan of 65 degrees is equal to the opposite, which is 35, over the adjacent, which is AB. So we can be able to calculate our AB from this. So that was the idea of this question. Oh, guys, sorry for that. I thought I put the eraser already. So if we do this, we can calculate our AB. Just like the previous case, if you cross multiply, it's going to be AB, the tan of 65 is equal to 35. Then we divide. So AB is going to be 35 over the tan of what? Over the tan of 65 degrees. So that's AB over this over the tan of 65 degrees. So by doing this, we are calculating what? AB. So that is our AB in this case, which was going to give us 16.321 millimeters. Now that we have our AB, let us take this. We have got this now. Our AB, we calculated this. So AB, we calculated this. This is 16.321 millimeters. So guys, we can formulate our Y, or we can find our Y in that case, because we said Y is the difference between these two, CD and AB. If I remove AB from CD, I remain with Y. So it means I can have this Y. That is missing here. By doing this, I'm done. So Y is equal to CD minus AB. CD, 19.621 minus AB, 16.321 again. So that was going to give us the value of Y, which is going to be very small value that we are obtaining, 3.3, approximately 3.3 millimeters. So with this, let us take this and conclude. Therefore, our X is equal to what? Therefore, our X is equal to 2 times the radius. Remember, our radius from the diameter, we divided and get 12.5. So it's 2 times 12.5 plus 2 times Y. We got Y as what? 3.3. I hope the concept of 2, you are getting it, to say this side is identical as this side. So you calculate one side only, all right? Then plus 125. So this was a combination of X. Everything that we have there was giving us X. So it was a matter of finding those that are giving us X. We're done. So that was going to give us 156.6 millimeters. So that was the idea of our question there. So that is how we are going to have these in our final exam. Expect to meet questions of this nature from the beginning. I hope you watched from the first part or from the first class. Make sure, if not, that you do watch those ones, so that you'll be able to understand each part of your syllabus, how and what exactly do they need you to understand. Mechanotechnics is a follow-up. You just need to follow the stages. This, okay. And these ones, you can even see that you play around with your geometry, you play around with your formulas and those diagrams, the idea of it. By just looking into the diagram, are you understanding this diagram on its own? Some of these are not formulas, guys. You don't need formulas here. You need to understand your diagram, interpret it. Can you be able to interpret? If you are able to interpret your diagram, you are done. So this is it, guys, from Mason African Motifs. Till we meet again.